Welcome back to the channel. In the previous episode, we discussed that in the forecasting competition introduced there, the expert who correctly inferred the true underlying distribution for each test day and submitted the distribution's expected value as her point forecast of the day lost to naive forecasters when the error metric was anything but mean squared error. Within the next several minutes, and using concepts from the field of Bayesian decision-making under uncertainty, I will explain the main reason she wins under mean squared error. Let's understand this by focusing on what happens in the first test day. The organizer has the true underlying distribution for the day, vertical axis plausible values and horizontal axis the associated probability densities, has sampled a single point from it, but that point, which represents the true value for the first test day, is not shared with the participants. They are asked to submit their forecasts for the day. The expert has correctly inferred the underlying distribution, but she does not know where the true point is. She has to decide which point from the distribution of that day she should submit as her point forecast for the day. I mentioned in the previous episode that she decided to submit the expected value of the distribution. In other words, its mean, without discussing why that value, or in general, how one should decide on which point to submit. Given the distribution for the first test day that we already saw, the left plot here, suppose our metric is squared error. To decide which point to submit, the fundamental question that one should ask is something along this line. What will the error be if I decide to submit y tilde equal to, for example, 1.5, the dashed line, and the true value y turns out to be, for example, the red dot? Again, what will my error be if y tilde, the dashed line, is submitted and the true value y turns out to be the red dot? The phrase turns out to be is essential here, as we are uncertain about the true point. Note that the dashed line is a point that we can potentially submit as our point forecast, a potential decision that we don't need to commit to, and the red dot is just one sample from the distribution. So we first pick a potential decision point denoted by symbol y tilde, sample points like the red dot whose value is denoted by symbol y, and for each y calculate the squared error between y tilde and y in the middle plot. While we are sampling more points and calculating the error for each, we will also keep track of the average error of the points sampled so far in the right plot. We will keep sampling more points until we reach a point where sampling further points does not change the average error. Let's see how this works. We have our first sample. Calculate the error for it. So far there is only one sample, so the average error in the right plot is the same as the error we just calculated. Sample the next point, calculate its error, and update the average. Keep sampling more points until the average error does not change with more samples. That converged value is the expected value of the squared error loss for a given y tilde. What we have done here is nothing but numerically estimating the expected value of our stochastic loss for a given y tilde. Now we make a new plot of the expected value as a function of y tilde, which will give us the expected error for each decision point y tilde. A lot is happening in this scene, so let's pause and review it one more time. We pick a y tilde as a potential point that we can submit as our forecast. For each y tilde, we sampled from the distribution different points y, which represent a plausible true value. Add to the second plot the error between y and y tilde, and update in the third plot the average error for the points sampled so far. Once that averaged error does not change with further sampling, we pause sampling and add the final averaged value to our last plot. Next, change the selected point y tilde to, for example, 2.5, and repeat the same process to get another point in the bottom plot. If you do the same process for a sufficiently large number of y tildes and samples, you will get a plot like this, which again shows the expected value of the squared error as a function of different points belonging to the distribution. Recall the underlying distribution for the first test day that we started from. In the left plot, find the point with y tilde equal to the expected value of that distribution. You see that the point corresponds to the minimum of the expected squared error. In other words, under the squared error loss, the expected value of the inferred distribution is the optimal point. It minimizes the expected error. This result can be derived formally by writing a stochastic optimization problem. Let's first make the distinction between related but different symbols clear. Capital Y is our random variable that follows distribution P1. We want to find point y hat from the distribution that minimizes the expected value of the squared error loss. The way we will find that point is by evaluating the loss for different points y tilde from the distribution. Simply expand the term inside the brackets, take y tilde squared and 2y tilde out of expectations because they are not random variables, but rather particular realizations of the random variable capital Y. From the first derivative test, which states that the first derivative at the location of a minimum will be 0, note that the objective function will be minimized for a set of y tilde values that satisfy this equation. So we need to set the first derivative of this term with respect to y tilde to 0, which results in y hat being equal to the expected value of capital Y. This is the formal confirmation of what I stated previously, which is under the squared error loss, the expected value of the inferred distribution is the optimal point. Going back to our competition, the main reason that the expert won when the metric was mean squared error was because she submitted the expected values, which, as we now know, are optimal under the squared error loss. She lost under the mean absolute error or MAPE metrics because the expected values are not optimal under absolute error or absolute percentage error losses. In the next episode, we will discuss which points are optimal under those two losses. Before ending this episode, I want to mention that here I presented a proof demonstrating that the expected value minimizes the squared error loss when there is a single distribution. I then applied this result to a forecasting competition that featured multiple distributions, with each distribution corresponding to a different test day. I asserted that the reason the expert won under the mean squared error metric was due to her submission of the expected values. While this extrapolation is valid in many real-life forecasting scenarios, there are special cases where it may not be applicable. To address this, I will be uploading supplementary material to the channel's homepage and GitHub repository. If you have any comments or questions, please do not hesitate to reach out. Alright, that will do it for this episode. Thanks for watching and see you next time.